Welcome back to The Explainer. So today we're popping the hood on how these massive large language models actually get trained. We hear about trillion parameter models in the news all the time, right? But the physical reality of building them requires some truly mind-bending engineering. Let's find out how it actually works.
All right, let's dive right into this. We're going to cover the giant model bottleneck, figure out what pipeline parallelism actually is, talk about bursting the pipeline bubble, look at advanced schedules, and finally, bring it all together with synergistic 3D parallelism.
Okay, part 1, the giant model bottleneck.
So I want you to think about this question for a second. How do we actually train models that physically cannot fit on the world's most powerful individual computers? This is what engineers refer to as the memory wall in AI training. It is a hard physical boundary that stops naive training approaches dead in their tracks.
Based on estimations from the Megatron LM research, it's wild. If you're trying to train something like GPT-2 Large, or the much larger Llama 2 7B and 13B models, it's not just the static parameters you have to store in memory. You also have to store the dynamic activations, the gradients, and the optimizer states, like the first and second moments. The required GPU VRAM absolutely skyrockets, completely blowing past the max memory capacity of literally any single GPU on the market today.
Now, if you're familiar with distributed systems, you might be thinking, hey, just use data parallelism. And sure, partitioning a training mini-batch across multiple devices is super scalable. But here's the catch. It fundamentally fails when the model itself is just too big for a single device. Slicing up the dataset doesn't help one bit if the actual neural network simply cannot squeeze onto one worker. We need a completely different game plan.
Which brings us to part 2. What exactly is pipeline parallelism?
So pipeline parallelism is a technique where we split a massive model across the layer dimension. The best way to visualize this is to think of a factory assembly line. Instead of trying to build an entire car at one crazy congested workstation, you put different sequential stages of the neural network on different GPUs. Device 1 processes the first few layers, hands the output off to device 2, and so on. It is an incredibly elegant way to bypass those single-device memory limits.
Here is how this actually runs in practice, heavily pioneered by frameworks like gpipe. First, you split the model into stages. But the magic happens when you divide your mini-batch of data into smaller chunks called micro-batches. You push these micro-batches down our GPU assembly line. You evaluate the forward pass, that's the F, and then later you backpropagate the gradients, the B. By pumping these small micro-batches through one after another, it acts kind of like loop-on rolling. It keeps the flow optimized and the assembly line moving as smoothly as possible.
Moving on to part 3, bursting the pipeline bubble. Now, if you map out a gpipe schedule charting the forward and backward passes across, say, 4 devices over time, you're going to notice something problematic. Massive gaps where devices are just idle. We call these pipeline bubbles. While device 1 is finishing up its backward pass, the other devices are literally just sitting there doing nothing, wasting precious compute time waiting for their turn or waiting for the entire pipeline to flush out.
The crucial takeaway here is that pipeline parallelism natively takes a massive hit on efficiency because of these bubbles. There's a bubble time fraction equation that shows this fraction is entirely dictated by the number of pipeline stages versus the number of microbatches. To shrink those bubbles down to a reasonable size, you'd need impossibly large batch sizes, which honestly just don't work mathematically or practically for most tasks. And if you don't use large batch sizes, you suffer from devastatingly low scaling efficiency.
It really comes down to a stark contrast between active computation time and idle bubble time. An active GPU is doing what it's supposed to do, crunching dense matrix multiplications, pushing your AI model toward convergence. An idle GPU? It's just standing in an empty conveyor belt waiting for the previous stage to hand over data. And at the scale of supercomputers, that idle time literally translates to millions of dollars in wasted hardware and electricity. So let's fix it. Part 4, Advanced Schedules and 1F1B. Data from PyTorch's Torch Titan framework brilliantly illustrates how much of an impact better scheduling makes. When you transition from a standard 1F1B schedule, which is just one forward, then one backward pass interleaved, to more advanced techniques like interleaved 1F1B and zero bubble schedules, the gains are huge. At a massive 512 GPU scale, a zero bubble schedule jumps to 125 words per second compared to just 96 for standard 1F1B. They are fundamentally rearranging the execution order of these microbatches to intelligently fill in those idle, wasted gaps.
Now, you're probably wondering, why not just use pure asynchronous 1F1B? Because in theory, running asynchronously pretty much completely wipes out those pipeline bubbles. But the literature notes a major caveat.
Convergence and training stability are mathematically not guaranteed when you calculate gradients asynchronously. You risk getting a bad model, and that quality degradation can easily outweigh a 20% performance bump. Given the insane financial cost and time required to train large language models, rolling the dice on mathematical convergences is simply a no-go for most AI teams. They absolutely need guaranteed stability.
And finally, Part 5, Synergistic 3D Parallelism.
3D parallelism is where it all comes together. It's the synergistic combination of data parallelism, tensor parallelism, and pipeline parallelism. Now, tensor parallelism, which we didn't dive deep into today, slices the model within a single layer. It has fantastic scaling efficiency inside a single server node. Meanwhile, pipeline parallelism acts as the interlayer factory line connecting those nodes. When you orchestrate them all together, research like the Megatron LM paper demonstrates scaling up to 512 GPUs, hitting an absolutely staggering 15.1 petaflops of sustained performance.
To put that into perspective, the DeepSpeed framework team said it best. Our latest results demonstrate that this 3D parallelism enables training models with over 1 trillion parameters. That is the awe-inspiring scale we are operating at right now. The incredibly technical pipeline scheduling and bubble-bursting techniques we just walked through aren't just abstract computer science theory. They are the direct enabling technologies for the massive, trillion-parameter AI models that are fundamentally transforming our world today.
Which leaves us with a pretty provocative question to ponder as we wrap up this explainer. As our software algorithms squeeze every last microsecond of idle time out of these GPUs, what exactly happens when the models inevitably grow another 1,000 times larger? Will we need 4D or 5D parallelism? This synergy between physical hardware limits and software ingenuity is truly an endless frontier. Thank you so much for joining me today. Keep learning, and I'll catch you in the next one.